model for this is the set of x plus yj, where x is complex and y is a positive real number. And there's this metric on it here. So if this is unfamiliar to you, you can also try to generalize to hn, and then you can take n to be 2. So actually everything I'll say also works in this setting, but I'm just going to focus on h3 here. Okay. So the reason I write the elements like this is that then you can view them as quaternions, and this gives rise to an action by PSL2C, which is by linear fractional transformations. So you do this, and then it's important that you make note that multiplication is not commutative. Okay, so this gives a nice proper action, and it preserves the metric, and blah, 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 blah. So, okay. So like we do with H2, you can take quotients. So we're going to do the same. So I'm going to fix gamma to be finite index and torsion-free inside PSL2 set of I. You can also do some other groups like this, like other imaginary quadratic orders. So I'm just going to stick to this one for concreteness. Okay. So this gives you M, some three-manifold, which is the quotient by gamma. Okay. So just to have an example, something concrete, you can take this congruent subgroup here, some congruent subgroup. Like with modular curves, the simplest ones, they're like a Riemann sphere with a point removed. So in this case, the simplest examples are like a tree sphere with a codimension 2 subset removed. So in this case, with a closed curve removed. So there's topologists who compute these kind of things, and you can find out this is the curve. Okay, so essentially you think of this as being embedded in R3, and then you add a point at infinity. And then you remove this, and that is topologically M in this case. So some people have worked this out. Okay. So we've seen a lot of special cycles now in this conference, so now I'm going to give you even more. Okay. So arithmetic surfaces. So these come from binary Hermitian forms. So these are expressions of this kind, and maybe I should say what the coefficients are. So A and C, those should be integers, and B should be, in this case, a Gaussian integer. So attached to such a guy, if it's positive definite, meaning that the discriminant, which is this expression, is positive, then you can define a surface in M. And again, there's some adjectives, blah, 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 blah. It's some surface in M. And you can imagine it's described in some way similar to what Eugenia said in her talk. Okay, so we have some natural surfaces, and Kudla and Milsom, they made precise in what sense it's natural, so it's what they call a special cycle. So again, blah, blah, blah. I'm not going to go into what a special cycle is, but it's some natural notion. And more generally, you can take intersections of such surfaces. So you have surfaces in M, you can intersect them. This also gives you special cycles. So you can do double intersections. I'm going to do that in a second. You can do triple intersection also, that gives you points, but we'll not look at that. Okay, yeah. So now you can see it's going to be a long slide because it starts at the top. So special geodesics, these are the intersection components of two arithmetic surfaces. So in general, you will intersect in some finitely many components. So now we just consider one component. And it turns out this is a geodesic. That's one of these properties of the arithmetic surfaces. Okay, so you have two cases. It's either going to be a closed geodesic. This happens most of the time. And it turns out I was quite surprised when I discovered this, and I think my supervisor was as well, that you don't get all closed geodesics. You only get some of them. So they're characterized by the fact that the trace is real. In this case, the trace is then an integer. This also has some geometric explanation. So, yeah, 5 minutes for me. So it means that the holomorphic is trivial. Let me not say that. Okay, but you get some of them. And actually, it's by results of Zarnak and Wakayama, it means that it's only 0% of all closed geodesics that you get. So it really shows that these are very special in some way. Okay, the other case is you can get an infinite geodesic. So in this case, it connects two cusps of n. Or in the example you saw before, you connect 2 points in this curve here. So this happens not as often. Okay, this is what I wanted to draw. So a fact is that, and this is kind of similar to the observation of Rickards that was also mentioned in the last speed talk, that there's this angle of intersection, and what happens is that, okay, you do this intersection, and you get some geodesic. So now you can look at the normal vector to each surface, and it turns out that if you move around on this geodesic, then the normal vectors will always intersect in the same angle. They are called theta here. Okay, so this I thought was quite interesting. So now we're going to use this to define some numbers. Now we get to the linking numbers from the title. Okay, so I'm going to fix S as surface in M, with the boundary being a special geodesic cycle, so meaning that it's a union of closed geodesics as before. Okay. And then I take T to be a positive definite symmetric matrix. So we've seen this many times in this conference that now we're going to get to these Siegel modular forms of genus 2, so now we consider some matrices. Okay, so then I define what is the linking numbers, and I'll try to explain in a bit if there's time why this is called a linking number. But okay, we consider this number iota Ts, and it's the sum over the intersection number of C prime and S, where C prime is sampled in the following, like the most natural way. So you sample pairs of arithmetic surfaces where the equation has discriminant T1 and T2, and where the angle of intersection is related to the off-diagonal entry T0, I guess in the same formula that we saw earlier today. Okay, so somehow we naturally sample over the most natural families of geodesics that you can get it this way, and then we consider the intersection number with S. Okay. So then the results are as follows. So the first theorem is it explains how to construct a canonical explicit function that are called G asterisks, and it depends on tau, which is a variable in genus 2 Siegel upper half space. So we've seen this many times, so I'm not going to define it. And then there's a C, which is a special geodesic cycle as before. So before we said C was the boundary of S, so this function does not require that C is the boundary of S. It works for any closed special geodesic cycle. Okay, and I know it doesn't look very canonical or explicit here, but you're going to have to take my word for that. So the main theorem is then that if you take sort of natural generating series of these numbers here, iota T of S, and then you add this function here, which is some analytic function, this transforms as a Siegel modular form, in this case of genus 2, and the weight is 2 and level 4. So it's some kind of mock modular function for Siegel modular forms that you get. Okay, so if you don't like mock modular forms, I also have a concrete application, which I think is quite nice. So using a Hege-bound strategy, you can get then a bound on these numbers. I think I'm pretty much out of time, but yeah, I think that's quite nice. So here you really use the explicitness of this function to get bounds related to this function, and then you use the modularity to use the Hege-bound method, and then you combine those two things. So I will stop here. Yeah, thank you.